So hello, my name is Gabriel. Thank you for coming. I'm going to start off with a couple of disclaimers. Disclaimer number one, this should be fairly obvious since we're at a Kotlin meetup, but this presentation will be based on typed languages. If that's something you don't have experience with, I think you should be able to follow just fine, but you might get a little lost in the low-level details at the end, but I think it'll be okay. The second disclaimer is that the purpose of this presentation isn't to change behavior. Like, I don't expect you to hear this presentation and start writing code completely differently tomorrow. There's this thing called Conway's Law, which some of you might be familiar with. It's a managerial thing, and it's a very fancy way of saying that if all you know is a hammer, every problem looks like a nail. And so the purpose of this presentation is merely to give you a different perspective and sort of, stimulate your thinking juices and food for thought. So how spicy will this get on the scale of butter chicken and vindaloo? This isn't actually, I didn't think of this, a guy named Sregi did, so thank you to him. We're going to start off easy and work our way up. The end won't actually be that spicy, it'll be code, but just there's not really time to sort of delve deep, so I'll be flying through, and it's possible that if the topics discussed will be new for you, then it's possible you might feel a little bit lost. I'll try and share the code through Slack or something like that, so you can take a deeper look on your own. But yeah, if you feel a little lost at the end, then that's completely okay. So let's start with the butter chicken part. Let's start with a social experiment. If I could ask you to take out your mobile phones and scan this QR code, or alternatively you can go to slido.com and enter the code that you can see. I have to wait for you to scan it before I can flip over and start the actual polling. And you'll be given 3 questions. The questions will be describing scenarios where something went wrong, and then some reaction to it, some error handling basically of that situation. And you'll be asked to rate it if you're happy about it or not. I'm not asking you about how happy you are that the mistake occurred, right? So like the first question will be, my car broke down, something. So I'm not asking you about how happy you are that your car broke down. I'm asking, if your car broke down, how happy would you be that the situation would be dealt with in the way it is? So you should see the first question pop up. Okay, perfect. So I'm going to give you guys a couple of seconds. So not very popular, I would say. So a couple of seconds more, 9 people voted. Okay. I'm going to assume that everybody who's going to be voting, oh, okay, so still some things coming in, but I think we can pretty much call it in, call the result. So I'm gonna stop this one and start up the next one. Okay, so pretty clear cut here, even more so probably, because there's no cool Elon Musk feature involved in this one. So I'm gonna kill this one in the third and final poll, and then we'll switch back to the presentation. Controversial. Interesting. Okay. Perfect. Awesome. Thank you. So I'm going to kill this now. We'll come back to these later on in the presentation, and I'm just going to jump back in here and continue on. So that was the butter chicken part. Congratulations, you made it. Now, before we actually talk about exceptions, I want to talk about goto. And when I say goto, I don't mean the version that you might be familiar with back when you started programming in C or something similar, where there was some goto construct that was occasionally used. I'm talking about the full-blown historical goto, where you could just jump from any part of the code to any other part of the code, wherever, in the same function or not. The goto you, or most of you, have probably encountered back in C, you could only jump in the same function. You couldn't jump outside the function. But the historical goto that you would have, I'm not even sure in what language is BASIC maybe or something like that, you could just jump wherever. So this version of goto is bad. And the reason I say that is because it was banned. It can't be found in any modern language. Now just a quick show of hands, which of you, who agrees with this? Who would agree that goto is a bad thing and that it was a correct decision that it was banned? Okay, a couple of people. Okay, awesome. Why? Say again?
You lose control over what is hard to reason about.
Okay. It's hard to reason about. Can you go a little bit deeper than that? What does that?
So, it's hard to trace back. Like, what if you can go anywhere? Then there are no guarantees about. Say even catching exceptions or handling errors.
Interesting. Okay. So, would you say it's a readability problem, or is it an actually practical problem?
I would say it's a little bit of both.
A little bit of both. Okay. Interesting. So, who of you have heard the term spaghetti code? Does that ring a bell? Yeah. Now, what do you imagine? I'm assuming you imagine something like this, right? So, I would ask, is spaghetti code the reason why goto is bad? Would you agree with that or disagree? Just sort of gut feeling-ish. Okay, yeah. I actually don't think that's the reason. And I'll tell you why. You can simulate the same type of situation you would get with goto without using goto. So imagine you have like 5 different functions. I'm sorry, you're going to have to imagine because it would take too long to write down. And you're in one function and you have a goto that jumps to a second one in the middle. Then you go 3 more lines and there's another goto that jumps to a third one, and it's this complete crazy mess. What you can do is you can take the body of each function, merge it into a very, very long function, just copy paste the code like one block after the other, and wrap each of them in an if-else statement. And what you will be if-elsing over a switch statement, which you will be switching over, is an integer state. And basically that state represents the label where you want to jump to. So for instance, if you would be in the middle of the first block, which would represent the first function, and you would want to jump or simulate jumping to the second one, you would just set the state to 2 and call the function recursively. You would call the function recursively, you would be at the beginning, you would fall through the switch statement or the if-else, fall through to the block, and start executing there. And it would have exactly the same semantics as if you use goto, but without using goto. But at the same time, we're not batting if-else statements because they have this property, right? So it must be something a little bit different that causes goto to be so hated that it was actually banned. And to give you an idea why that is, I have to show you a couple of pictures. And we'll be talking about control flow, but it's much easier to talk about the pictures. So this arrow over here represents sequential control flow. This represents an if, obviously. This is a loop. This is a function call. And this is goto. So just looking at the pictures, just intuitively, what's the difference? Can you see a difference between the group on the left and goto on the right? What's the difference? Like, try and name it or express it. Sorry, go ahead.
Vertical and the other is horizontal.
Well, a function call is also vertical. It goes to the right.
Getting back.
It's getting back, exactly. So the difference is that on the left-hand side, whenever the arrow comes in, it also comes out, every single time. As opposed to the other one, goto, where the arrow goes in, but it never comes back. Now, why would this be important? Well, the reason this is important is that when things go in and go out, I can abstract away from that and imagine it's just sequential flow. I don't really have to care about what's happening inside those blocks. I can just pretend like it's going through. And this is really important because this is the principle, or this underlies the reason why we can think about code as black boxes. So, for instance, think about print line. Like, who here knows, have you ever opened this function? Have you ever looked inside? I haven't. I have things to do. And we don't have to care, right? I mean, this is a function that you call, it does its thing, it returns the control of the flow back to you, and that's it. I don't have to look inside to be able to tell what it's going to be doing. But imagine if there was a goto somewhere in that thing. You would have to open up the function and you would have to find that goto, you would have to understand under which conditions the jump would happen, and you would have to prepare for that in some way. That would be absolutely crazy. So, goto is bad because when you use it, you break your ability to do black boxes. You break your ability to think about things in terms of black boxes, which is pretty darn important because we're dealing with software that is impossible to fit on our heads. So this is an important thing for us to be able to do. But it's actually even worse than that. Because even if you don't use goto, even if you have an agreement with your entire team that nobody will ever use goto, the mere fact that it's inside your language, it exposes you to the risk that someone will. And so when you're calling a function, say a library function, maybe not something that your team wrote because your team, writes proper code, but maybe you included a dependency. And there you don't know if that person used goto or not. So you have to open up every function you call and look and see if it's calling goto. And if those functions are calling other functions, then you have to open up those functions as well, and over and over and over again. And you can see that this is getting like crazy. It's impossible to write code like this. So not only is goto bad because it breaks your ability to think in terms of black boxes when you use it, but it actually breaks your ability to think in terms of black boxes just by being in the language. That's a very different, much worse type of property. Now, these things aren't, what I'm saying here, this isn't like a new thought. This has been thought of and discussed long ago. You probably know this guy, at least the text and the pronunciation. It's Dijkstra, so now you also know how to pronounce it. He kind of looks like Walter White Sr. And what he was interested in is how to write code back in the 60s or something like that, how to write code that is too large to fit in your head. Back then, that wasn't really common. Today, that's completely common. And he realized actually that goto was one of the reasons that you couldn't, that it was difficult to do. And so he wrote this paper. It's called Goto Statement Considered Harmful. And it's a one-pager. It's very short. And it was completely controversial. Like, people went really crazy, and there was this huge war between proponents of goto and detractors of goto. And it was not like Donald Knuth. You have probably heard of him. He was in the camp who supported goto. And it was, give programmers toys and then try to take them away from them, they won't be happy. So it was really kind of intensive. But as history, history is written by the winners, so we can see that the decision was made that Dijkstra was actually right, and that it's not a good idea to have goto in our languages, and so we kicked it out. Now, does this mean that it's impossible to use goto responsibly? Of course not. Like, all the people who are in that camp that wanted to keep goto were probably using it responsibly, except for a couple of percent. But you can't guarantee that it will be, and that's the problem. Now, how is this solved? Well, this was solved by taking those reasonable applications, which were usually if statements, loops, and function calls. That was what goto was used for originally, and encoding those in the languages, and just kicking goto away. And history went on, and all of us are completely satisfied with that, and nobody would ever think of using goto for one of these applications. So having said that, what is this? No. Yes, but not yet. Now think about it. When you start up a new thread, it has exactly the same behavior as when you're using goto. Because if a function starts up a new thread, you as the caller don't know it. And you have to open up that function and figure out if it's doing something messy. If it suddenly started 5 threads and just, did whatever. You can't know that until you open the function. But even worse than that, you don't even actually have to do it in order to be exposed to that risk. Like, just the fact that we have the ability to start threads wherever we want, whenever we want, we are at the risk of somebody somewhere doing something that they shouldn't be. Now, obviously, most people are normal, and most people don't start up a new thread when they're calculating the sum of 2 integers or something like that, but there's nothing stopping them from. And again, you can control the quality of the code that your teammates write, but you can't control the quality, or it's much more difficult to control the quality of code that you download off Maven or something like that. So when you really think about it, starting threads have exactly the same properties as goto. Now, again, as with goto, does that mean that threads can't be used responsibly? Well, of course not. Like, everybody here has probably started a new thread, and I'm sure that all of the situations where it was proper use and there was no shady business involved. But again, you can't guarantee that everybody will. So how was this problem solved? Does anybody know? We're all Kotlin people, so we should know. Stepan knows. Yeah, I know Stepan knows. Nobody else knows, really? Like, are you just shy, or nobody knows how this was solved? This is the reason why structured concurrency was invented. The thing that structured concurrency does is it restricts your ability to start up tasks on different threads by saying that you can only do it in a special block. You can imagine a lambda in Kotlin, that's Cortin scope, right? Every thread you start, you have to wait for it for finish. That block doesn't exit until all the threads have finished, or it doesn't have to be threads, all the childs, whatever you spawned, have finished. And if any one of them fails, the whole thing fails and reverts and go back. You know all of these properties from Kotlin. But this is exactly the change that allowed you to, and you can see it on the picture really well, that allowed you to bring those errors back together and allows you to reason. And that's the reason why structured concurrency is so powerful. It's because it allows you to do whatever you want, and I can still call a function and be 100% guaranteed that when that function returns, that there's no other monkey business going on. So now, what is this? You probably all know this is exactly exceptions. And if you think about it, exceptions have the same property. If I throw an exception, I, as a caller of that function, have no idea that that's going to happen, problem number one. But problem number two is, if I want to find out, I have to open that function and look. And then I have to open all the function it calls and looks. I remember back like a couple of years ago, I was trying to figure out when I call in Mongo, I call save, what exceptions could be thrown by that call. And I killed an afternoon and I still don't know. Because how do you find out? Now again, does this mean that exceptions cannot be used responsibly, or does this mean that you shouldn't use exceptions? Well, no, absolutely not. But you should understand, at least after today, that they have the same properties as goto and thread spawning. So what about checked exceptions? Now I know we're in a Kotlin community, so this is, I have to be a little careful bringing this up, but I'm assuming all of you know what they are. Would you say that these solve the problem intuitively? Show of hands, who thinks that checked exceptions would solve this problem? One person, two people.
Sort of.
Sort of, okay. Can you expand on that?
I don't think that it solves every problem, but it's some way of little bit, at least, have some list of what can I expect.
Okay. So it makes it a little bit better. Yeah. And I would tend to agree with that. Just out of curiosity, not many of you people rose your hand. Is that because the implementation of checked exceptions in Java is shitty, or is there another reason why you didn't raise your hand? Because I completely agree that the implementation in Java is wrong, but that's not a problem of checked exceptions in general. So imagine a world where checked exceptions in Java or in whatever world are implemented correctly. Like there are no problems with lambdas, no problems with generics, and all the other things we know. Would that change your mind? Would you think that that checked exceptions solve this problem in such a world? Again, show of hands, just real quick, intuitively, gut feeling. Stefan does, okay. Interesting. So, let's dig into that a little bit deeper. What if I transformed, I said exceptions are the same thing as goto, so what if I transformed that question and asked, what if we allowed goto, like the super hardcore goto of the 60s, but just mandated that each function that uses it has to say so, has to declare I'm using goto. Now, would you feel that that would be a good way to go? Probably not. But why? I mean, that's strange, right? Because I think that some of you sort of felt, as do I, that checked exceptions they definitely help, but should sort of solve the problem, because I know that it's a checked exception, so I know that it's going to throw, the function is going to throw. So why doesn't this solve? But when I do the same thing with goto, it suddenly feels all wrong. So why is that? What's the actual problem that's going on? And to answer that, let's look at your responses. So the first question was, you're driving your car, check engine light comes on, and it drives off into, let me see if I can show the, perfect. And it drives off to the mechanic. Most of you were not satisfied with this. Why? Try and explain why that was.
Complication. It's complication.
What is?
When the car is broken and I need to end it and I'm late and so on. I think.
Okay. I think. Sorry, go ahead.
You give up control, right?
Interesting.
Your choice.
Interesting. Very good.
You're more
more aware of the situation, so we can kind of guess what's the correct situation. So it really depends.
Exactly.
On the context.
Exactly.
Maybe with the case with the doctor, you can't know like all the details. Here.
Interesting. We'll get to the doctor, but very good point. Very good point. All of you. I think basically all of you said the same thing. Did I understand you correctly? Control. Like, how does the car know? I might be driving somebody to the hospital who's dying of a heart attack. Like, I don't care about the checked engine light. I need to get to the hospital now. How does the car know? The car can't know. I'm the one who should be in control because I'm the client of the car. I'm calling the car, and the car is wresting control away from me. Looking at the second example, something a little similar. I was actually expecting this to be sort of 50-50. It was even more clear-cut than the car, which was surprising to me. Can you think of a way to tweak this situation so you would be much happier? It's not really, like, in reality you probably couldn't do it, but a very small change to the way they handle errors where you would be much happier.
You could try to deliver later.
Possibly, yeah, but maybe you're leaving for vacation in 2 hours and that's even worse, actually.
Or you can choose another pickup point.
Basically, precisely. They would ask. Just ask. Call me and ask. Like, this happened. This, by the way, this is based on a true story. This actually happened to me. I live probably 2 blocks away from the Alza warehouse, and because I'm lazy, I ordered, for them to deliver it to an Alza point that was even closer to me, and they missed it, and they, delivered it way completely outside of Prague, and I was just like, you could have just taken it back to the warehouse, and I would have gotten there. That's like, it's 20 meters further than the Alza point, but they didn't call, and it's understandable why. So we've seen in both situations that the issue is an issue of control. We don't feel comfortable when things take control away from us, especially if those things know less about the situation than we do. But if you think about it, that's exactly what exceptions do. If I call a function which divides 2 numbers that knows nothing about my business, nothing, and never will, and that function decides to throw an exception, and it will completely unwind the stack and completely destroy whatever, and maybe it's not a problem. Maybe it's, okay, so we have it 0, so we just log it or whatever and continue on. Now, obviously, you can fix that. You can surround it with a try-catch and just continue on, but is that really the default that we want? And as we can see in the real world, that's not the way we would want things to work. So, checked exceptions don't actually solve this. Now, they do help, but it's the same problem, it's only documented. Going back to the example with the car, it would be basically, the car does that, but it's just written in the manual. Well, I mean, that's great, but the reasonable default would be to offer me, hey, checked engine light, do you want me to drive you to the mechanic? That would be great. And again, with exceptions, it would be great if they didn't unwind the stack. If you had the ability to, if you had the option to, but you weren't required to, that wasn't the default, and you weren't required to surround it into the try-catch and changing that behavior. Now, as I said before, there are other, on the JVM or in Java specifically, there are, excuse me, other problems with checked exceptions. They were not implemented in a very good way. They screw up generics, they screw up lambdas, as probably all of you know. That's why Kotlin ditched them. There's actually another problem that I would like to talk more about, and I won't. Ask me over at the end during questions. It has to do with the fact that the way checked exceptions are designed, they actually leak abstractions, and we can talk about that at the end if you're interested. Now here's an interesting thing. We went through the first 3 Slidos, and basically all of you agreed that that was not, those error handling situations were not a good idea. But this question was very different. Like, a lot of you were meh, but a lot more of you thought that this was good design. But that's interesting, because we just said that we don't like when control is taken away from us. So why is this different? Why? I'm sure that some of you answered unhappy in the first 2 and happy in this one. So those of you who did, can you elaborate why you feel differently here?
Life-threatening. So
life-threatening?
Unrecoverable state.
Okay, interesting. Unrecoverable.
I think that in this case, the implementation can tell the severity of
precisely
the situation.
In other words, there are some. Sorry, go ahead.
It's the context.
It's the context. So in other words, we can see that there are some situations which are so severe that just, destroy the universe. Like, we got to deal with this right now. There's no time to deal with control. So there is actually some nuance and some situations where we feel that it is appropriate to take control away of the caller. Now, if you apply this thinking to generally errors, like what type of errors there are, you come to the conclusion, or you maybe don't, but I did, that there are actually 4 kinds of errors, and I write 1 plus 3, you'll understand that in a second. The first type of error isn't really an error, in my opinion, and it's just some well-defined state in your domain. So for example, validations are a favorite example of mine. Validations are just a computation where you send some input and it sends back a list of things that wouldn't work, that would cause an error if you send a form or something like that. But the calculation that does the validation isn't itself, like if it finds a missing piece of data, that in itself is not an error in the context of that validation. Imagine if you're typing something on the front end, and whenever you change a field, it sends off a request with the entire payload, but just to check it, just so you can highlight the fields in red which are missing or whatever. So that endpoint that error call didn't end up with an error message, right? It didn't return 500 or 401 or whatever. It returned 200. It was okay. It did return something that we intuitively feel are like errors, but in that context, they really aren't. So I would say that this first category, things that are well defined in your domain, aren't actually errors, even though they describe something that we as humans think of as being errors. There's another category, which are scenarios outside your domain. Now, this is typically, internet is out. Putin nuked my data center. Database was wiped, whatever. Now, again, you might think, well, actually, I'm going to talk about this in a second. So that's the second type of error. The third type of error are sanity checks. So these are assertions on input. For example, I expect this list to always be non-empty. So the first line of that function would be asserting that that list is non-empty, and if it is empty, then that's an error. Another situation would be invariants that I expect not to be violated. So for example, I could have a database and I could say that if this column is true, then this column should never be null. But then somebody can just write whatever insert, and if I don't have database constraints, then that can basically happen, and I can load data in my application where that happens. So I need to assert for that. And then the final type of error, which are the complete fatal, something went completely wrong, out of memory, typically. There are a couple of others. So how should we model these situations? How should we model these errors? Well, it depends. It depends on the language. And there are roughly 2 different kinds of language, or 2 different categories of languages. One category is the one that we're probably mostly familiar with, and they're the ones that you can see at the top, and there are many others. And those use exceptions, as you guessed. And then there's a second category. Kotlin falls sort of in the middle. You can do a little bit of both. It's up to you. But there's a second category of languages that take a very different approach to these, to error modeling. So in the languages that we're familiar of, basically everything is an exception. Maybe someone would model the first scenario differently by not throwing an exception and doing something else. But I would say that typically, on average, the average code base that you encounter, at least in the JVM world, most of these situations are solved by exceptions. Now, the other category of languages say something different. They say that the first 2 categories are actually not supposed to be modeled by exceptions, but they're supposed to be instead modeled by actually constructing values and just returning them, as you normally would. Now, we'll take a closer look at that in a second. You might have noticed that the last 2 types of errors are still modeled by throwing exceptions. It's not always called exceptions. In Rust, it's panic. I think in Haskell as well. Some other languages have different terminology, but basically it's exceptions. You might have also noticed the in parentheses in constructors, and if you're interested in that, ask me later during the Q&A. So I would just like to say that I honestly don't know how many of you have heard of this other approach of dealing with errors, but it's not something that's new. Like, most of you have probably heard about Rust because Rust is sexy right now, and this is what Rust does, but this idea has existed long before Rust, and there were probably languages before Haskell, but Haskell is the probably oldest and at the same time most well known, and that has been here since the 90s, so that's like 35 years or something like that. So this is definitely not new. So let's think about a little bit about why exceptions are actually used, because they wouldn't be used if they didn't have something, good about them. And the reason exceptions are used is because they short circuit. Now what that means is that I can write code, and if something bad happens, I can just throw an exception, and shit happens, and I don't have to worry about it. So basically I can concentrate on my happy path, and I can trust that error handling will be dealt with somewhere. Now that's actually I hear your ironic laugh and I feel you. And that's actually like the problem, because we don't know where that error will be handled, if it will be handled, what will happen in that error handling and stuff like that. But let's not go into that. The writing experience, the experience as a developer of using exceptions is great when you're writing the code. Not when you're reading it, but when you're writing it, because you don't have to worry about anything. You just, something went wrong, throw exception, and I can just continue on and deal with it some other time, which means never. So you could say that error handling using exceptions is basically a combination of three things. It's values, because exceptions are values. You can put messages in and some other values, whatever you want, so they're an actual object. They also have short circuiting, so that's a second fundamental property of exceptions. And the third one, which is the one that we don't like, is stack unwinding. It's the fact that when it's thrown, then it's the whole stack gets unwound and we lose control and jump somewhere completely different, which is exactly what goto does. Now, error handling in these languages are values, as we said, and like I said, I'll show some code in a second so you can imagine something a little bit more concrete. Short circuiting, kinda. It depends on the language, it depends on the syntactic constructs that you have available. Definitely to some degree always, but to what degree it depends on the language. But no stack unwinding. So how does that look? This is the part where we get a little bit spicy, but again, just because we'll be going through code and I don't want to spend a lot of time here, because it would, like this would deserve its own presentation, just this alone. So I'm just going to fly through, give you a high level overview. Feel free to ask anytime and I'll explain further. And then we can take a closer look through Slack or something like this. So I modeled a very simple business scenario here where we have some account, an account has an order, and we want to calculate how much we should bill the customer for that order. And the way we do this is, so just quickly to fly through, we have an account that has an ID, we have an order that also has an ID, and it's associated to an account, and it has a value. This represents a value in some money type. And the way we're billing is we're basically taking a percentage of that value, and that's what we bill to the customer. So we're basically multiplying these two values together, and that gives us the result that should be built. And this information is contained in some pricing object, which is again associated to the account, as we would expect. And we have some services that I didn't bother implementing that get an account, give an account ID, get the pricing, get the order, and get all orders for the account. Now, given those, we want to implement three different situations. The first situation is just getting an account name. Super simple. We just fetch the account, access the name, that's it. The second one is calculating the charge for the order given an order ID. So this is actually interesting because we first need to fetch the order, then we're able to get the account ID, use that to fetch the pricing, and then we can calculate the actual charge we're going to charge the customer. Now, what's important here, although it might sound a little weird why it's important, but you'll see in a second, or I'll hint at it, is that these two lines are dependent. I first need to calculate the order in order to be able to to get the pricing. In other words, I can't flip the order of these two lines. Now, you'll understand why that's important in a second. Now, the final situation is we have an account ID and we want to get the total for all the orders. Now, we could probably call this one, but I'm specifically implementing it here like this. So we use the account ID to get the pricing, we use the account ID to get the orders, and then we do the simple calculation. But here, unlike here, these two things are independent. I could have done this before I did this. So there's a slight difference in the type of problem that we're modeling here. Okay, perfect. So this would be the case if we were using exceptions. These are silently thrown in the background somehow. We don't know about it. Something is happening. Now, let's take a look at how the other languages that we talked about earlier model this situation. So what these languages do is they basically define a sealed interface that has one of two instances. One instance represents the calculation went fine, everything is okay, and they contain the result of that calculation, whatever it might be. And the second type contains or represents an error happened, some type of error happened. And they again contain some sort of object, a different type, that represents that error and probably contains, some information. It could be exception, it doesn't have to be exception, it can be whatever you want. Now, you can see this modeled here. I'm using the Rust terminology, so I'm calling the sealed interface result and the two versions of it OK and error. If you used Haskell, probably Scala as well, some other languages, this is usually called either. And the value that's incorrect, that represents an error, is is called left. And the OK one is right. The reason it's called this is because right as in correct, so that's why right, and left is the opposite of right. It's a little play on words. I don't know how comfortable you are with covariance and contravariance, so this might be a little scary for you. Nothing as well, you can just completely ignore it. It's not important for what we're talking about right now. It just makes working with the code a little bit easier. And here I just define some sealed interface that will represent the error instance that we will be putting over here, and I just define some random value. I don't think it's ever even used anywhere. That's not really important. But you can just imagine whatever you want for this interface. Now, as we can see right now, all of these functions are suddenly returning an instance of result. So we can see that they fail, or they can fail, and depending on the type of this, if it's going to be OK or error, that will tell us if if everything went OK and we can proceed with the calculation, or if not. So how do we model the situations that we talked about? So basically, what we do is we just switch over the type, the easiest thing we can do. So we fetch the account and we check. Is it an error? Well, then let's just return it. That's it. If it's an OK type, great. Then we can access the value. That's this value over here. So that's going to be the account, and access the name, and then wrap it again in an OK instance, because we're also returning something that can fail. So basically, if get account fails, then we also fail. If it doesn't fail, then we also don't fail. And we apply the exact same logic in the other situations as well. So here we fetch the order. If it's OK, perfect, we can use the order to get the pricing. If it's OK, perfect, then we do the calculation, wrap it in OK. And if an error is returned from the order, we return that error. If an error was returned from if an error is returned from the pricing, we return that. If an error was fetched from the, order, then we return that. And again, exactly the same thing in the last situation. But there's a slight difference here. When there was an error in this part, when we didn't manage to fetch the order, that was basically it. There was nothing we could do, because we needed the order in order to be able to fetch the pricing, because those two lines were dependent. But in the other situations, those lines are independent. So when we try fetching the pricing and we fail, we can still actually try and fetch the orders. Now this is interesting, because unlike exceptions, with exceptions, if an exception happens, then it's fail fast, then it fails immediately, the function exits, and that's it. But here you have a choice, and you can do more steps and maybe accumulate the errors. If an error would happen here as well, then we could accumulate the errors and give more information to our caller. Now this is super useful, for instance, in validations. When you're doing validations, you don't want to return the first thing that's wrong. You want to do the entire most wide possible check and return all of the errors. So just to illustrate that with this approach, you actually get a choice here. And you can or don't have to take advantage of it. Now, obviously, like if we really wrote code like this, it wouldn't be very comfortable. It wouldn't be comfortable for us, and it definitely wouldn't be comfortable for the people who are reading the code. So there's actually a little change that we can do that makes this a little bit better. And I'm going to try and do a very quick, so just to understand, this over here is actually the signature of this function, right? So it accepts an account that may or may not fail, and a function that transforms an account into a string. That's the getter, basically, and it returns a string something that either didn't fail and contained a string, or some sort of error. Now, when you look at the signature like this, it probably doesn't remind you of anything, but I'm going to do a very, very, very quick replace, and I'm just going to do this. And if you look at this, does this ring a bell?
It's a mapping function.
It's a mapping function, exactly. Map. You've probably all heard of map. Excellent. Now that's not a coincidence. What about here? I'm going to do the same replace. Does this look familiar?
Looks like burrito.
It's a flat map.
Flat map, exactly. Flat map. Now that one probably or might not be as well known as map, I don't know, but definitely, yeah. Now this third one can be basically thought of as a generalization of map. So what map does, it takes an account, a single one, and a function that accepts a single parameter, and it applies that function to each element of the list. What this does over here is it takes, oh, I'm sorry, I screwed up the replace somehow. It's supposed to look like this. And what this does is that it has two lists and a function with two parameters. So it takes one from each of the lists, plugs it into the function, and then we get the result. So it's basically the higher, like, multi-parameter version of the simple map that we know. But this one is not commonly seen with lists, but what you probably do know is zip. And if you used creating a pair as this second function, you would get exactly zip, or the zip that you know. Okay, so knowing that, we can actually extract and name these functions. And this is the part that I'm going to fly through a little bit. You can take some time later and really think about that I did this correctly, but this is how those things would work. So this is map, this is flat map, this is map n. Basically, it's exactly the when statements that or the when expressions that we saw before. It's nothing else than we already showed. And when you use these functions to rewrite it, this is what you get. So not as crazy as what we had a second ago, but still pretty crazy for people who are not used to this type of programming. Okay, end of code demonstration. So let's look at these two, at the results next to each other. So on the left we have the situation where we used exceptions. On the right we have the situation where we used values. So we can see that we're definitely returning values. There's no stack unwinding involved anywhere. We actually kind of get short-circuiting, because if you look at the flat map over here, if this fails, this lambda never gets executed. And if any of these fails, this also never gets executed. So you kind of sort of get short-circuiting, but not really in the sense that we're used to. So when you look at a balance sheet of these two approaches, you get a lot. And it depends here how important each of these things are for you. For me, it's super important. For you, it might not be. So, take away from it what you will. For me, one of the best things is that you have expressive type signatures. I look at the signature of the function without reading the body, and I immediately know that it can fail, and in what ways it can fail, as in what the sealed interface in the error type is. So that, for me, that's super useful. It also encourages treating error states as part of your domain. Now, your mileage may vary on this, but I feel that when you're writing exceptions, you just, it's just some exception and you don't really think about it that much. But when I'm actually writing data classes, I think a little like, does this conceptually make sense? Does it make sense on this level of abstraction where this function is defined? And it maybe, hopefully, forces you a little bit to be a little bit more careful about defining your error states, which is an important part of your modeling process. And unlike checked exceptions checked exceptions, you can use it with any higher order function. So you can use lambdas, you can use map, flat map, stream API for those of you who are still unfortunate enough to write Java like me. And it doesn't screw up everything. So that's also a super great property. And finally, we don't have the stack unwinding, so we retain control. But there is a downside that I think we'll all agree on, and that is that it looks very different. Now, as a person who has actually tried writing this style of code in this way, like literally maps and flat maps, I can tell you that it's actually not as horrible as it looks. You get used to it. It's a little bit like I'd call it the Lisp factor. Everybody who doesn't read Lisp or write Lisp is completely befuddled with all the parentheses, but when you start writing it after 4 or 5 days, you don't even notice them. And there's a very similar effect that happens here, because you'll actually see that there's a very sort of simple visual transformation you can do to translate between these two situations. So when you actually start writing this, it tends to sort of melt away and it's really not that big of a problem. But when somebody else comes, like your boss for instance, and see that you're writing this, then you're in for a lot of trouble, because it does look pretty scary and very different. But what if it didn't have to? What if we had something else at our disposal where we didn't have to pay the price of it looking different? Now, this is an example of what that could look like. For those of you who know Arrow, you're probably aware that this is taken from Arrow, but you actually don't need Arrow to do this. Like, this is much more general than Arrow. This is completely general, and it's not dependent on Arrow in any way. But this is something that we unfortunately don't have time to go into today. I am planning on making another presentation where we'll go much deeper into this, maybe sometime after the summer vacation. So here it's just an appetite whether so you can imagine. But I'll just say that this is exactly the same behavior or type of code as this flat map version, but without the downsides. It basically looks exactly like the imperative version we wrote before. So, to recap, first we talked about goto. We explained why goto is bad, or I hope I explained it in a way that was understandable. We also realized, or at least for me this was a realization, that it's not just the fact that when you use it, it's bad, but it's actually bad just by existing. And we also saw that threads and exceptions have the same property. Now, we talked about checked exceptions, and we saw that they help. It's definitely better when you have them, assuming they're implemented correctly, which they're currently not. But they don't actually solve the problem. And a train of thought from there led us to thinking about what types of errors we have, and that there are 3+1 errors. One of them isn't really an error, because those are states in our domain. Then we have states outside our domain, and then we have assertions or run-type checks, sanity checks, and then fatal errors. And various languages, Rust, Haskell, Scala, and some others, approach the first two types of errors, or modeling the first two types of errors by returning values and not throwing exceptions, while basically all languages throw exceptions in the second two types of situations. And we can do that, like there's nothing, you can even do that in Java. It's a super pain because Java doesn't have covariance and contravariance, so like actually working with the types and convincing the compiler that what you're doing is actually okay is a super pain in the ass, but it can be done. There's nothing for stopping you. And it's much easier in Kotlin, of course, because it has a reasonable type system. But doing that, I mean, it's great, we do get some benefits, but we're left wanting more. We want to be closer to the imperative version that we're used to. Now, some reading references. Basically, like 65% of this presentation was plagiarized from this article over here. This article is actually quoted many times by Ivan Elizarov. And this was basically where structured concurrency was invented. This, or at least as far as I'm aware, this was the first time that structured concurrency was implemented. He actually implemented it in Python, and that's the reason why today we have it in Kotlin, and Java is catching up, and maybe in 10 years we'll get it there as well. It's a great article. It's just one of those articles that I keep reading and rereading every year. It's absolutely awesome. It's a longer read. It's probably 20 minutes. It takes a while, but it's great, and I highly recommend that you go read it right now. And the other one that I would like to mention, and that I mentioned before, was the article by Dijkstra. It's one page. You can read it in 3 minutes. It's an interesting read. It's also interesting just because like the way he expresses himself is very different than the way we express ourselves now. So it's like in the era of modern politicians, it's a refreshing read for that reason, if nothing else. Questions?
What do you think about the new, what's it called, the union type errors in Kotlin 2? That's one pause.
I think so the reason why, or one of the reasons why checked exceptions are so fucked up is that they actually enable you to do union types. Because when you think about it, you can write any exception types in the throws declaration, and they don't have to be from the same hierarchy. And that's actually the problem, because it's the only part of Java, it's the only part of the language that allows that. And so when you want to use any other part of the language, like generics, for example, it's difficult to plug that in. For example, you can't write a generic function where you say something like, whatever this is thrown, then rethrow it. No, you can do that, but you can't do throws two different exceptions. That's very difficult to do. And so for me, at least, or from the way I think about it, I feel that the fundamental reason, or one of the fundamental reasons why checked exceptions were such a catastrophe, is that they allow you to do this, but don't support it in the rest of the language. So my answer to you, or to your question, is dependent on how it's going to be implemented. If they circumnavigate that, if they find a way to implement it and allow it to be usable with the rest of the ecosystem, then I'm fine with it. But I'm skeptical that you're able to do that, because, for instance, one of the things you would need in able to do that, you would need for it to bubble up through higher order functions. So for instance, when you have map, like generic map on lists, that doesn't throw an exception in and of itself. But if you plug in a function that does throw an exception, then map should throw an exception as well. So how do you do that? How do you express that this function throws only if it's inside throws. And it's the same problem with the union types. So I'm not opposed to the idea, but I think it's very sensitive to how it's going to be implemented. I hope that answers your question.
But isn't it actually very similar to like declared either one type, the other type? It's very, I thought it was actually like convertible between themselves.
Not really, because when you have the result type, you're constrained by the type hierarchy. Like I can't have a result type that has an integer or a string. You can do that in TypeScript, but you can't do that in Kotlin. I mean, you can have the any type, but you're not going to do that. But the error types, from at least what I understood, you could do that. You could have error types that aren't constrained. Now, I'm not saying it's impossible to implement it without these problems of checked exceptions, but I think that it's possible to implement it with those problems. And if they do implement it with those problems, then it's a problem. I don't know how they're planning on doing it. I actually responded to that thread. There was some discussion going on, and then 30 other people responded, and I haven't been bothered to read it since. But there is active discussion going on there, so feel free to if you have specific ideas, to write them there. It seems to me like they're really listening, and they're open to pointers on how to do this correctly. But it is a very controversial feature from what I've understood. Great question, thank you.
So corrected question, because from my experience, from not so small code base of some 70 services with Arrow, most of the time developers tend to use some common parent error in left type, so we completely lose the one of the possible benefits of the type expressiveness of what you can extend. Because you get error time. So what's your experience with this problem of losing the type expressiveness of errors as others in your code bases?
Well, a couple of disclaimers. My experience isn't broad enough for me to be comfortable to answer this with certainty, but I have a couple of thoughts. So thought number one, if you want to screw up, nobody can stop you. Like you can use any everywhere, and you can do it, and there's nothing stopping you. Now, the question is, what is the benefit of not doing that? What is the benefit of actually having the error hierarchies and stuff like that? And so one benefit obviously is expressiveness, right? Like I can look at the errors and it tells me something about the code base. Now, for me personally, that's a very big plus, and one that I am willing to suffer for a little bit when I'm writing, because for me it's just great down the line, and I tend to optimize reading experience versus writing experience. But it is much difficult to write, much more difficult, or not difficult, but just a pain in the ass, because you have to do, I didn't talk about this here on purpose, but when you throw or create an error of a certain type in a function, when it bubbles up in the parent function, you have to map it to that type, and it can get pretty crazy pretty quickly. In the next presentation that I do, I'll talk about how Rust solves this problem. I think it's a very nice solution. So there are pains involved, and you just have to think about if that's worth it. Another thing that I would say, for people for whom that expressiveness is not something that they would want, then I would say decide based on if there is a part of the code that is reacting to that specific type. So if I have some function and I'm declaring, data failure, whatever that might be, then there should be some part of the code somewhere else that reacts to that is literally, if it's an instance of data failure, then I do something, restart the database or something like that. Yeah. And if that's not there, then it's a question like, do you really need it?
I think that it will be mostly useful in the domain part.
I tend to agree.
Where you are throwing some domain states.
Definitely. I 100% agree.
I hope that union types could bring some nice way of solving this problem. Because if I'm, for example, booking and canceling booking, get different domain errors.
What I hope is that at the very least, being part of the language, being an actual language feature, it will at least force people to okay, so they went all they went through all the work of implementing this as a feature, so I guess there's something there, maybe I should look under it. But if you're a bad designer, this isn't going to save you.
It's slowly turning into a workshop, and I really like it. But I also don't want Gabriel to,
I actually, if I can have 2 more minutes, there's a very quick ending to the presentation that I'd like to tell. Because I wanna leave you with something to think about. So when we went through the code, we encountered functions that you probably already know from lists. So we talked about map and flat map, map-n, you probably don't know, but that's the signature and it can be thought of as generalization to map itself. And list, of course, expresses a multitude of values, and then we also saw that the result type, or either, whichever it might be, has or permits the same type of definition, or the same type of functions. And it turns out there are other data types that permit these functions, for instance, future or promise, whichever language you might come from. You can define the exact same functions there, and they often are defined, except they're usually called something else, like flat map is usually and then, I think, map is, I don't know what it is. But they are semantically exactly the same thing. You could define a type that represents a value that's been validated, a container type that's been validated. This is actually basically either, just named a little bit different, and you could again define the same functions on that. You could have a value that represents some value with a log associated to it. And you could look at transformations of these values and combinations of these values. So for instance, in flat map, you start out with a value that has some log and produce a new log. So you need to do some type of concatenation in that flat map. And I could go on and on and on. And for those of you who are a little more versed in functional programming, you've probably recognized at least some of these types. But these types are completely different. They have completely different semantics. They describe completely different situations, but they permit the same functions. And so my question to you is, and what you can think about after we're finished here, is this just a coincidence, or does this model a deeper pattern that's involved in this? This is the end of it.